All right, here we go. So I just sent I posted the answers to the worksheet due today, but it's not posting until later. I won't give you the time because I want to make sure you do it on your own. I don't want you to watch the video of me going over it and then you just copy the answers down and then send it to me, right? So you'll get that later tonight. So do it first, obviously, then check your answers. All right, so I wanted to do a sample Regents question with colligative properties, so here we go. Compare the freezing point of a mixture. Let me see, make it a little bit bigger for you. Compare the freezing point of mixture 4 at 1 atm to the freezing point of water at 1 atm. So automatically, if I take, I can't do that, not yet. Let's see. Here we go. I can do it this way. Okay, if I take the little picture. All right, so mixture 4, so automatically I know mixture, I know water, so colligative properties say at a solute, boiling point goes up. At a solute, freezing point goes down. So I already know the answer to this question is the freezing point is lower. But let's look at it here. So mixture 4 is KNO3 and water, right? So we got 10 grams of KNO3 and 10 grams of water. So that is the most concentrated solution. So I'm just going to review some things with this. The answer to this question is, and how you would answer it, is the freezing point of mixture 4, right? So freezing point of mixture 4 is lower than water. That's how you would write it on a Regents. I know that's really messy. Freezing point of mixture 4 is lower than actually, you know what? Then you should write lower than the freezing point of water. So you should actually really spell it out, than the freezing point of water. And again, I probably shouldn't do this kind of stuff, but I'm just going quick writing FP instead of writing freezing point. On a Regents, write the words freezing point. So I should do it. If I want you to do it, I should do it. But freezing point of mixture 4 is lower than, it doesn't matter what that mixture is. That's what colligative property, it's kind of the easy part of the concept, is you could put anything you want here. This happens to be KNO3. It could be anything. The mixture is always going to have a higher boiling point, lower freezing point than water. At a solute, boiling point goes up. At a solute, freezing point goes down. And, again, that's just a good sample Regents question. I don't know why this doesn't, whatever. So there you go. That's a good one. Typically, they're multiple choice where they say, here, they'll give you something like this. They'll say, all right, so you have, maybe they'll say, all right, NaClAq versus H2O. And they'll say, which of the following is true of NaCl? And they'll give you 4 choices, and they'll say higher boiling point, lower freezing point. So they'll say higher boiling point and lower freezing point. And that's the answer. So if that's number 1, that's the answer. But then the other 4 choices, they'll say higher boiling point, higher freezing point. Lower boiling point, lower freezing point. Lower boiling point, higher freezing point. So they'll switch to those words, or they'll say increase. They'll say NaCl has increased boiling point, decreased freezing point. So they might use the word higher, lower, decrease, increase. The point is, at a solute, boiling point goes up. At a solute, freezing point goes down. And the only other thing I'm going to mention before I talk about Henry's law here is if you take something like salt versus calcium chloride, this one is going to have a higher boiling point, lower freezing point than this one. Why? This has 3 moles of particles, 2 Cl minuses, 1 Ca plus 2. This has 2 moles. So that's like the hardest way they could ask that on the Regents. They ask about boiling points and freezing points of these 2 solutions here. So you have salt and calcium chloride. This one is going to have higher boiling, lower freezing point because there's even more particles disrupting the forces. So again, at a solute, boiling point goes up. At a solute, freezing point goes down. All right, Henry's law. about solutions here. Basically, I'll keep this very simple. What Henry's law states is the pressure above the solution is proportional to how many dissolved particles are in the solution, and this goes for gases. So I'm actually not going to write the definition, but here's a good way to understand, and I have a video too. But if you have two containers, let's say they are sealed, and then you have gas up here, right? So here's the say 20 particles there, 10 particles there. What Henry's law basically states is, and let's say these are dissolved CO2, right? So in here we have CO2 aqueous, like in soda, which you should not drink, but soda has CO2 in it. So let's say this is soda down here, all right? Dissolved carbon dioxide. The pressure above the solution, the greater it is, the greater the pressure, the more particles will be dissolved in solution. That's what Henry's law states. I don't always think definitions are the best. So here's how I kind of do this. Right? All right, room pressure. We got 1 atm pushing down on this solution over here. Well, I have 10, let's say 10 moles of dissolved CO2 over here. Well, if I increase that pressure, okay, we could actually maybe shrink this area, right? Maybe we have like a big piston and we push down on it. But for now, let's just say we have a higher pressure. We double the pressure. So now we have 2 atm, all right? Think of atm as like a weight, like in that Boyle's, that gas law lab, Boyle's law and Charles' law. The more weight squeezes the air in the syringe. So same thing here. If you increase the pressure pushing on this liquid, more carbon dioxide is going to stay dissolved. Basically, it can't get out. Okay, think of the air up here, think of it as CO2. So let's say you have CO2 gas up here, okay? Because that is in the air, right? So if you have CO2 pushing against CO2 in solution, the stronger this CO2 is up here, the less likely these CO2 particles can get out. All right, so think about like this, the surface of the liquid or the water or soda, which you shouldn't be drinking. Imagine that's kind of like the battleground here. So the CO2 is trying to get out, right? They're trying to get out. And then the CO2 on the top is trying to get in. So if this is stronger than this, so 2 atm is definitely going to have a higher pressure than the vapor pressure of the, not the vapor pressure, but the pressure of the gas trying to get out. So if you have a greater pressure up here pushing against the CO2 trying to come out, it's not going to work. The CO2 is going to stay dissolved. Whereas when you decrease that pressure, some of these are going to leave, the CO2 is going to get out, and therefore less of it is dissolved. That's what